quickly, an overview of how to study for your OChem final. For your OChem final. So how to study, how I recommend you study is, first, I think you should just do a one-page summary of every chapter. So for each chapter, make a short review, just like what are the big ideas, what do I need to jog my memory about. We do this together in class a lot, but essentially just what's everything we covered. And at the beginning of each set of notes, I have an outline that pretty well goes over it. So you can try to remember what you did in that chapter and then check the outline for yourself. And then I would maybe do a few practice problems from each chapter if there's something that you're like, I don't really remember that thing. Just to sort of jog your memory. And then when you've done that, honestly, I would sit down and take this review that I'm about to do, the video key for this practice exam. I use it as quiz 8. Because I really want you to use it as a practice exam. So I think you should sit down and take this, give yourself 2 hours. That's how much time you're going to have on the final. You'll need to bubble in your answers so you can sort of maybe practice, like, you know, every time you get an answer, flip to another page and write it down, like A, B, C, D, or whatever. Because you'll need to bubble in, so account for time. And then grade it. And you can use that to see basically like, okay, how much did I understand? What would your grade be if you sat down and took the final? So overall, how did I do? What's my grade? Is it where I want it to be? If it's not where I want it to be, what was I missing? And when you see what you're missing, don't just review that question, but look at that concept. And try to give yourself a review of the concept either by looking back over our notes, watching our class videos, finding another resource online. Look over that concept, and once you've understood, like, okay, this is the concept, this is what I'm missing, I think I understand it, do some practice problems for that concept. And you should be able to find those in your PLTLs, in your homework questions, in our in-class questions, in your old exams, quizzes, recitation. You have lots of options for those. Also, Klein's Organic Chemistry as a Second Language has a lot of good questions. And then see, okay, am I getting it? Would I be able to get the question right on the final exam this time? So that is kind of how I recommend taking this practice test. It allows you to see where you need to focus your studying on, because maybe there are some things that you already have down really good. But I will say, if you are guessing and you're getting things right, I would review those things too. So as you're going through, if you don't know about something and you're like, I don't know, but I think it's this, put a star by that question too and treat it the same way. I put but it should be treat it the same way as the ones you got wrong. So look at that concept, do some practice problems, make sure you really know why you're getting it right and why you're getting it wrong, so that you understand the full scope of like this concept. So this is how I recommend that you study for your organic chemistry final exam. The more practice problems you do in each area, the better. There's lots of resources for organic chemistry practice problems, but this is how I think that it's wise to study. And then, of course, this quiz that I'm about to do, this quiz 8, it's a practice exam. So I'm going to go through each one and sort of see how I approach these questions, and so that can help you as well. So let's start here with this one. Select the structure of benzyl methyl ether. So benzyl is like a benzene ring, but typically benzyl has a bend in it, so it's got an extra CH3, that's how I remember it. And then methyl CH3, and then ether is an oxygen. So I'm going to look for an oxygen that has a methyl on one side and a benzene on the other, but a CH2 before the benzene. So I'm not even looking at my answer choices before I've drawn the structure. So these have 2 benzenes, so that can't be it. This has a CH3 on one side, but then this benzene does not have a bend in it. It's just a benzene ring. So that would be phenyl methyl ether. This right here has a CH3 here and a benzene. So this is probably my answer. Benzene with a CH2 attached to it. This one has 2 benzenes and this one has 2 benzenes, so neither of them could be right. So as long as you know to at least look for one methyl, you could narrow it down to these 2 structures only. And then if you didn't remember between benzyl and phenyl, that's fine, but you at least have it down to 50-50 getting it right instead of, 1 and 5. Okay, next question. Which of the following, I forgot to say, you will have an IR or an NMR chart on your thing, so you can always look at that. Which of the following represents the predicted approximate chemical shift and coupling for the hydrogens associated with the arrow? So when I look at this, the first thing I'm thinking is these are similar to what you might expect to see from, I wish I had a chart handy so I could show you. They'll be similar to alkanes, but there is a withdrawing group which takes electrons away, if you remember. And so as we take electrons away from a hydrogen, it shifts to the left. So it shifts to the larger numbers. So I'm thinking that it would probably be in the typical range that you would expect to see an alkane, which, let me pull this up. I think it's like 2 to 3, but I'm just going to make sure that I have the NMR chart in front of me, because you'll have that in front of you. But I will say, I give you roughly the range that it would be in, but I might not give you the exact range. I won't give you like the exact thing always. So even though there is CH3s on there, there's not CH3s directly adjacent to a ketone. So you have to kind of figure that on your own. So typically CH3 is estimated to be in the range from, or CH2 in an alkane chain is estimated to be in the range from 0 to 2. So I'm going to get rid of this 3 down here, and I'm going to say, all right, it could be in the range from 0 to 2. I think it's going to be towards the left of that range, just because I think that as it's getting near this ketone, it's going to be de-shielding it, which is going to shift it towards the larger numbers. So I think it's going to be in the larger numbers. So that's one thing I know that I'm looking for, and one answer I've eliminated. And the other thing I can look at is the splitting of this. So it's indicating this CH3 all the way at the end. So I'm looking at the one right next to it, determine the splitting. The integral of it would be equal to 3, and then the splitting is based on how many neighbors it has. So it has a hydrogen here and a hydrogen here. You can ignore that other little mark there. That was from earlier when I was just gesturing. So it has 2 hydrogens next door to it. So the splitting pattern is going to be equal to N, which is the number of neighbors. So neighbors is 2 plus 1. So the splitting is 3, so it'll be a triplet. So it'll look like this. Okay, so based on that, I'm seeing, all right, we have a quartet, a singlet, and a quartet. None of that makes sense. There's only one possible answer here, and that would be this shift being around 1 and it being a triplet. Okay, so that's how I'd approach that. What reaction can accomplish the following transformation in good yield? Okay, so when I see questions like this, actually, I don't know if I've talked to this class about it yet, but the way I process through is the first thing I do is I think about what kind of reaction could this be. And so I look for clues about what kind of reaction this could be. And so I think about actually all the way back to OChem 1, what did we learn initially? So I'm going to make a list of reactions. Is one, we learned acid-base reactions. And then the next thing we learned is, I think, substitution and elimination reactions. We did learn, let's see, we learned addition to alkenes. And in that one of the things we did was the H2, platinum, palladium, and metal. Sometimes people put that in the earlier chapter, but I try not to. Addition to alkenes, we learned radical reactions, some others of us did not. And then we also learned reactions of alcohols, how to make them, and then how to react them forward. We learned conjugated systems. So that'd be like Diels-Alder is a big one, and then 1,2 or 1,4 addition. And that was like, we talked about thermodynamic versus kinetic control. And then we went into electrophilic aromatic substitution, and then we did reactions of oxidation, reduction, and then we also did more reactions of ketones and aldehydes, and that included like the hemiacetals, amines, all of that. And then we also learned we've learned carboxylic acid reactions. So this is kind of an overview of the all the reactions you've learned in OChem 1 and OChem 2. So when I'm looking at this list here, and then I'm looking back at this reaction, I'm looking for clues that can give me hints for what it could be. So I'll say the first big thing that jumps out to me is an alkene. And so acid-base reaction, it could be that maybe. So I'm not going to eliminate that, but it's probably not going to be a substitution or elimination because I don't have a good leaving group. Could be addition to an alkene because we have an alkene in the beginning, so that's a good option as well. Radical reactions, I don't see it being a radical reaction because that usually makes a halogenation is what we typically use radical reactions for, so probably not that. A reaction of alcohol, maybe, because it makes an alcohol, and in that chapter we did review how to make alcohols. But it doesn't look like a conjugated system because there's one double bond, and not electrophilic aromatic substitution because there's no benzene. Not oxidation or reduction, really, because it's an addition before you would consider it an oxidation. It's not like it's adding bonds to alcohol, technically. I mean, I guess it is, but not in the same way that we talk about for oxidation or reduction. And then a reaction of ketone and aldehyde. Well, there's not a ketone and an aldehyde or a carboxylic acid. So I'm thinking it's probably going to be an addition to alkene to make an alcohol. And we learned 3 ways to do that. Oxymercuration, demercuration. Oh, well, they're listed here for you. Oxymercuration, demercuration is one way. Another way is acid-catalyzed addition of water. And then a third way is hydroboration oxidation. And each one of these has their own special features. This will add Markovnikov. Hopefully you remember what that means. It basically means the carbocation is the most stable. This will also add Markovnikov, but it doesn't have the possibility for rearrangement because it doesn't go through no carbocation mechanism. So no rearrangement. And then the last one is anti-Markovnikov. So then the alcohol adds to anti-Markovnikov. The alcohol would add to the last substituted side. So when I'm looking at this, honestly for me, the easiest thing to do is assume that it's H plus and water first. And I just see what happens. So if I do that, then I know that I would get my carbocation here. And then it must rearrange. So that tells me it's probably not oxymercuration, demercuration. But where the carbocation forms is where the alcohol ends. Sorry, I said the carbocation having rearrangement means it's not H plus and H2O. But the carbocation is on that same position where the alcohol would be. It didn't move. So that means that the Markovnikov position is where the alcohol adds. Anti-Markovnikov would be over here. So I'm looking for the one that does Markovnikov addition without rearrangement. So that must be this one. This reaction with NaOH, that's nothing. I don't think we've done anything where a base reacts with an alkene. So it's just there to kind of trick you. And so that's how I get to answer choice B. Okay, now what would the product be if the other answers, we already said D doesn't work. So we'll do A, B, or C. So we already said A would get that carbocation and then it would rearrange. And then the water would add there, and there would need to be a deprotonation step. So we would get OH2 plus, and then it would deprotonate. So that would be if we add acid-catalyzed hydration of water. And then if we did anti-Markovnikov, the alcohol would add out here on that side. So we would get this structure. Which of the following best represents the predicted approximate chemical shift and coupling for the hydrogen indicated with the arrow? Okay, so again, I'm going to look at what is my typical range for NMR, and this is a CH3. It's a CH3 next to an alkene, and alkenes, hydrogens off of alkenes are shifted up in the 2 to 3 range, but plain old alkanes are in the 0 to 2 range. So I'm going to assume it's going to be somewhere in that range. So probably not 5. I guess a hydrogen off an alkene could be a 5, but it's not directly off the alkene, it's next to the alkene. So I don't think it's going to get that high. So I don't think either of those are right. I think that would be the shift for something like that. So I still think it's in the 0 to 2 range, but the left side of that range again. And then I'm going to look at the splitting pattern. So if I look at my neighbors, it looks like we only have one neighbor. So the splitting pattern would be N plus 1, neighbors is 1 plus 1, so that would be a doublet. So it's going to be somewhere between these two. And I think this is kind of tricky, honestly. I think it would be hard for me to make a judgment call on this just from the information we have. But I think my instinct would be to go slightly higher, that it would probably be closer to the 2, because it is somewhat de-shielded by that alkene. But honestly, I think, oh, you know what is great is I'm looking at this NMR chart, and it actually has, I was not looking at my chart, I wasn't using my resources. It has a hydrogen that's 1 away from a carbon-carbon double bond. I wish I could show you it, but I just have it pulled up on my laptop. So it has this structure, HCC. So it looks like that. So this is the hydrogen that it's saying, and it's giving that range from 2 to 3. Yay, so my instinct was right. I didn't even realize it was on the chart. So I think it would be probably 2. So that's kind of how I approach these questions, is I first think about, like, in general, what would this shift be? And then I consider, so maybe it would help to write that out, like, typically, what is the shift of that functional group, of that hydrogen, of the hydrogen off of that functional group? And then the next thing I ask myself is, what about the environment? So, like, is there something that is going to shift it left or right? So further away from its direct environment. What about the rest of the environment? So that's why I said, like, okay, typically this is going to be from the 0 to 2 range, but because it's near this carbon-carbon double bond, I think that's going to shift it up, and I think it would be closer to the left side of that range. And then the last thing, once I've done that and I kind of have a general idea, then I'm like, okay, good to go. Good idea of that. The next thing I do is look at the splitting. Now, if it's easier for you to look at the splitting, you could do that first, but it would have essentially narrowed you down to the same first 2 questions. So that's kind of how I approach it. Okay, next question. What is the IUPAC name for the compound shown? Well, the first thing I always do is first name the parent chain. So for carbons is butane. And then I look at the functional groups, so carboxylic acid and fluorine. Actually, I'll do fluorine in purple. So fluorine is fluoro, and the number would be 3 fluoro. And normally you ask yourself, like, oh, how are we going to number this parent chain? But because there's a carboxylic acid and it's high priority, I don't have to ask that question. I know that I could start on the carboxylic acid side. And then so maybe I should have started with that, sorry. But then the carboxylic acid is, you drop the E and you add oic acid. So then I put it all together and make sure to consider alphabetical order. I don't have to worry about this time though. 3-fluoro-butanoic acid is the full name I would go for that. So I usually name it before I even look at the multiple choice questions, just because that kind of helps me be a little bit more confident that it's right. But if you're not sure, if you're like, I'm not positive, the first thing I look for is, are any of them not butane? All of these are butane, so that doesn't help me. We haven't learned anything called butyric acid though, so go ahead and get rid of options C and D. And now it's just between 3-fluoro and 2-fluoro. So we're assuming that butanoic acid is 1. So even if you weren't sure how to number it, if you're like, oh, do I start from the left or the right? If you can think about the higher priority group being the right one, then okay, higher priority needs to be the number 1. And then that puts our fluorine at position 3, so that's right. Butane, that's right. And oic acid, that's right. So answer choice A. So it can't be none of these, and it's not this one either. Okay, so that's how I approach those questions. The following transformation would be considered a what? Okay, so again, when I look at questions like these and I'm not sure, I would, here, let me erase the green markings on this. And I would come back to this list. I make this list out of my mind, and then I, so that it's like a study tool that I use, is kind of having this list handy in my brain. And then I, reactions of ketones and aldehydes, got. Reactions of ketones, aldehydes. So I'm going to come back and look at this list, and your iPad's handy because you can copy that, but if you are on a test or whatever, you can just flip back to that page. But for the purposes of this video, I'm just going to copy it, and then I'm going to come back down here and I'm going to paste it. Okay, so this is our list. This is our list of things that we could have to worry about. And so I'm looking at this, and it doesn't look like an acid-base question. And the reason I'm thinking that is the biggest thing I see changing is this aldehyde became a carboxylic acid. So an acid-base reaction would just move a proton or a lone pair. So I don't think it's an acid-base reaction. The substitution elimination is a substitution, just swap something out. Elimination adds a new double bond, so it can't be that. Addition to alkenes, well, there's not an alkene to start with, so not that. Radical reactions usually add halogens, not that. Reaction of alcohol, we don't have an alcohol, so not that. Conjugated systems, we don't have a conjugated system, so not that. Electrophilic aromatic substitution, no benzene, so not that. Oxidation reduction, ding, 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 ding. I'm seeing like, okay, we have 1 bond to oxygen, now we have 2 bond to oxygen. That's a possibility. Reactions of ketones and aldehydes, also ding, 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 because we start with an aldehyde, we end up with a carboxylic acid, and then that's the last question as well, the carboxylic acid. So I'm thinking about these chapters as what did we learn in oxidation reduction, reactions of aldehydes and ketones, in making carboxylic acids. And so I think it's going to be one of those. So based on everything that I just said in my brain, I can cross out addition, I can cross out elimination, and I can cross out rearrangement because we decided it wasn't any of those. Rearrangement is just a carbocation shifting, so that wouldn't make sense. So we know it's just going to be either reduction or oxidation. So we don't even have to think about reactions of ketones, aldehydes, or making carboxylic acids, which is nice. We don't have to worry about what reagents it would be, but we do know that it's in this vein of reduction or oxidation. So now we can narrow it down and think like, is this reduction or oxidation? Oxidation is adding alcohols or adding oxygen bonds, or really more broadly bonds to things more electronegative than carbon, and this is removing those. So if I'm looking at this transition, oxygen or more electronegative, we start with an aldehyde, and now we have an oxygen between the carbon and the hydrogen, which means we have 1 new bond to oxygen. So I'm going to say that is oxidation. Okay, Next question, and I'm not going to go through this whole thing again, but because we have the same option, so we know that it's going to be something from that list. Not an addition reaction, because we're not adding anything across a double bond, so I don't think it's addition. Not an elimination, because we're not making a new double bond. And maybe I should have started with this, but I'm looking at this transition. This thing became an alcohol. So how do we get an ester to become an alcohol? Well, we definitely reduced number of bonds to oxygen. So I think that's going to be a reduction. Rearrangement doesn't make sense. Okay. Which of the reagents listed below would efficiently accomplish this transformation? So again, I'm thinking we're in our oxidation reduction stage and we go from a ketone to an alcohol. That's the only transition I see. So this is a reduction reaction. And it's a ketone, which means it could be reduced by NABA4. I don't know why I said NaH. NABH4 or LaH. So when I look at my answer choices, I'm looking for NABH4 or LaH. So NABH4 is one here. LaH is one here. H2 and palladium, that's not one that we use for this. Just to jog your memory, H2 and palladium is H2 in any metal just turns the alkene to an alkane, but that's not one that's on here. And then more than one of these choices, that is seeming right to me, because for a secondary alcohol, we can reduce with any reducing agent. Or sorry, for a ketone, we can reduce with any reducing agent. If it was a ester, you could only use LaH. And if it was a primary, or like a carboxylic acid, I guess, and it was trying to get to an aldehyde, you could only use, certain reagents for that. So be sure to consider that. Now, this next reaction is essentially the opposite. We're going from an alcohol to a ketone. It's a secondary alcohol to a ketone. So what reagents do I know that can do that? All three of the reagents we know, PCC, Jones, and KMNO4. So I will say I get my list of what reagents it could be first, and then I look at my answer choices, because a lot of times the answer choices are just in there trying to trick you. So again, I'm thinking H2 and platinum's not right. Br2 and CCl4 is not right. KMNO4 is one. Jones, this should be Jones reagent like that. So I would say Jones reagent or KMNO4, either can do it. So we'll say E. Now, if this was a primary alcohol instead of a secondary, you wouldn't be able to use both of those. Okay, which reagents are capable of reducing the following ester to an aldehyde? So when I think about our oxidation reduction chapter, we looked at all these. Carboxylic acids, aldehydes, ketones, and esters. And one of the students said, if you only want a slice out of your cake, use NABH4. But if you want the whole cake, you use LaH. And so I am looking at this and thinking this is an ester, and so it is only able to react with NABH4. Now, if you want to go beyond just like not NABH4, sorry, LaH. I'm just realizing I misread the question. I was just so excited to tell you this. I was not talking about to an aldehyde, so that's my mistake. Whoopsie. This whole thing doesn't matter. I was about to talk to you about how you could know what could reduce what based on the features of the actual molecule rather than just memorizing it, but in the meantime, I'll say this is not asking about just reducing what's capable of reducing an ester. This is what's capable of reducing the ester to an aldehyde. And we did not learn that until, if you go back and look at our chart, that is something we learned in our reactions of ketones and aldehydes chapter. Reducing to an aldehyde needs a hydrogen that can only react once. So LaH with ester will reduce it all the way to an primary alcohol. It would replace both of these. It would replace your oxygen with a hydrogen, and then it would come back in and attack again and do that again. NABH4 can't reduce it at all based on what I just said. NABH4 is less reactive than LaH, less reactive than LaH. And because it's less reactive than LaH, it can only attack the easiest ones, the easiest carbonyl carbons. And so the ones that have the least steric hindrance and the ones that are the most electrophilic. So it can't do that because ester is not as electrophilic or reactive as aldehydes and ketones. Diol H, we learned, however, has only one hydrogen, but it still is strongly able to attack because it's not the different electronegativity on the atom. So Diol H is a good one. And then this would be a version, I think it's trying to mimic Jones reagent. No, it doesn't have chromium. I don't know. That's not one that I've ever seen, and neither is this. So I'm not worried about those. I'm only going to stick with the one I definitely know. Next one, what is the major product from the reaction of ethylbenzene with KMNO4? So let's start off with ethylbenzene. What does ethylbenzene look like? So benzene with an ethyl on it, and then KMNO4. And this is one of those reactions of side chains. This is where I expanded the capability of KMNO4 one more time and said KMNO4 is just going to oxidize everything it can. You can look up the mechanism for this if you want, but KMNO4 oxidizes to carboxylic acid, so I'm going to say it's answer choice B. And if you're not sure, if you don't have that in the top of your mind, you can think KMNO4 is probably not going to be able to break open a benzene ring. Very few things can break open benzene rings. So it's not going to be that, and it's not going to be that. We've never seen KMNO4 stop an aldehyde, so it's not going to be that. And if KMNO4 was in the presence of an alcohol, it would convert it to a carboxylic acid. So that can be a way you could kind of get to the right answer, even if you didn't have that memorized. And that's what I mean when I say use what you know to eliminate wrong answers. Don't just think about, oh no, I've never seen this before, and panic, but use what you know. Okay, next one. Predict the product for the reaction shown. NaBH4, okay, this is where I wanted to have this conversation. So if you think about lithium aluminum hydride, it has this, and this is negatively charged overall. And then boron has this. And so because the boron bond onto the aluminum is stronger, or onto the hydrogen is stronger, it's more electronegative, it's not as willing to attack as the LAH. So it only can be attracted to the most reactive. Whereas something that has a lone pair right here, it has an additional resonance structure where this is not positive. So the partial positive on this is less big than the partial positive on this. So LAH and NaBH4 are different in which one they can attack. LAH this is a weaker connection right here. So it can reduce everything. Whereas this is stronger connection, so it's not as willing to attack. It can only reduce the most reactive, which are aldehydes and ketones. So, and if you have a hard time remembering that, I do love the cake analogy, where if you're LAH, you can take the whole cake. If you're aldehydes and ketones, you can only take a slice for NaBH4. But this is the reason behind it, so you don't just have to memorize it. So now, if we're looking at this, NaBH4, so we know it can only react with ketones and aldehydes. So it's not going to react with this over here. It'll only react with this, and it basically acts as a hydride and converts this to an alcohol. So I'm looking for something that does not have the ester messed with, so it can only be 1 or 3. But then 3 has no change that's happened to it at all. So it can only be 1. So the answer must be A. None of these, rest of these are possible. Okay, next question. What is the hybridization change at the carbonyl carbon when a carbonyl group undergoes a nucleophilic attack? So if I have a carbonyl group and it undergoes nucleophilic attack, it goes from being sp2 hybridized right there to being sp3 hybridized right there. So sp2 to sp3. Which of the following resonance structure is not a significant contributor to the carbonyl group? Okay, so let's see. This first one is fully neutral, and it looks like a valid Lewis structure. So 1 is definitely a major contributor, so we can get rid of that because it's asking what is not a significant contributor. This next one has a negative charge on the carbon, so this bond break. This oxygen does not have a full octet. So that tells me that this is not as stable. And oxygen is more electronegative than carbon. So if one of them is going to be negative, it's not going to want to be the oxygen. So I think 2 is a probably pretty good answer. 3 had the carbonyl group. That's the curved arrow to get it right there. And so the oxygen being negative is more stable than the carbon being negative. So I think that is a better contributor. So I'm going to pick B. Neither 2 nor 3 is important. That's not true. 2 is a much higher more contributing, 3 is a much more significant contributor than something like 2. That's a very less stable reaction because it can be attractive to nucleophiles. It gets that carbonyl carbon positive. That's something we've talked about a lot. And then I wouldn't say all are significant contributors because that carbonyl carbon does not want to be negative if an oxygen is positive. So that's the least stable. So it's the very small contributor, not likely to happen. Okay, now we're back to an oxidation reduction question. And again, I know it's oxidation reduction because I see this LAH. So if I'm looking back at my list of all the reactions that we've gone over, well, if I'm looking back at that list, I know that it's not acid-base because LAH is not going to be giving a proton or stealing one unless there's an acid present, which there's not. Substitution, elimination, same kind of thing. So I've like gone through this list in my mind, and I know that LAH goes with the oxidation and reduction. And I know that LAH basically looks like this. And so then this must be attracted to this because it's negative, and that thing's positive, which will kick that bond up. And so we get a secondary alcohol. So let's see. First, I'm going to look to see what all has changed in these. I'm going to use my highlighter. So this CH3 should not have been affected by this reaction at all. So I'm looking for the CH3 to stay a wedge. We don't have that in this one, so I'm getting rid of 2. CH3 is still a wedge here. CH3 is not a wedge here, so I'm getting rid of that. So it's 1 or 2 are my options. And then I'm looking at these. Both of these have a secondary alcohol with a CH3. Oh, wait, no, I already canceled that one out. Both of these have a secondary alcohol with a CH3. It just looks like this is the enantiomer of that. And so then you have to ask yourself, what would the stereochemistry of this reaction be? So we've talked about this a lot before, but if you have something that's sp2 hybridized, this is flat. And if a nucleophile attacks it, it can attack it from either side, just like if you have a carbocation. And so then that means that you could get your nucleophile being a wedge or a dash. And either of those are possible. And so if you have a chiral center that is formed, you'll get a racemic mixture of both. So I'm thinking we'll have a racemic mixture of 1 and 3. So not of 1 of 2 because that one, 2, anything with 2 or 4 we can immediately eliminate. And if we immediately eliminate 2 and 4, then the only answer left is answer choice B. Okay. Your task is to synthesize this through a Grignard synthesis. Which pairs of compounds listed below would you choose as starting materials? So this is kind of tricky. Basically, for me, this one would be easier if I make the Grignard. I know this is a lone pair. I think about it attacking and what would happen. So if I attacked on this side, the O- would be over here, and there would be a new bond to the 6-membered ring. And we don't want that. We want the alcohol to be on the 6-membered ring, which means the alcohol, the thing that would give you the alcohol on the 6-membered ring is probably if there was a carbonyl on that 6-membered ring and then a nucleophile attacked it. So I'm looking for the carbonyl on the 6-membered ring, which we have in B and C. In D, we don't even have a 6-membered ring, so it can't be A based on what we already talked about, and it can't be D based on what I just said. So we've narrowed it down to B and C. Well, C has 2 6-membered rings and no 5-membered rings, so it can't be that. So now I'm going to do, if this became MgBr, basically we'd get rid of that and have a lone pair here. This would attack, that bond would kick up. I always do the reaction just to make sure that I didn't miss something, even if I'm pretty sure this answer choice is right. So it would look something like that. And then we'd have acid would be the next thing, but it doesn't ask like what reagents, it just says what pairs of compounds would you choose as a starting material. So you can assume you would add the acid later, so then I would choose B, because it would give me, if I added acid and alcohol on the 6-membered ring and a bond to the 5-membered ring. All right, homo-lumo diagram. So now we're thinking about butane, butadiene, 2 enes on butane. So butadiene looks like this. I'm looking for what the hybridization of each of these is. This is sp2 hybridized, 2 implied hydrogens. sp2, sp2, sp2. So if all these are sp2 hybridized, then they each have a p orbital that's not being used. So if I'm making the molecular orbital diagram, there are 4 p orbitals, each increasing in energy. And then the next thing I'm doing is counting up how many electrons could be moving between those. And the pi bonds are made up of electrons that are in these pi orbitals. So 1, 2, 3, 4. So the highest occupied molecular orbital is this one. It's the highest one that's occupied. So it has 2 electrons in it. Butadiene has how many pi molecular orbitals? It has 4 pi molecular orbitals. Same number as how many p orbitals it has, which is not an example of resonance. Oh, I will say for this, you should also know, like, in the middle of this is the non-bonding line. And if there's an orbital on the non-bonding line, if it's an odd number, that's a non-bonding orbital. And the homo-lumo gap right here corresponds to the amount of light that needs to be absorbed. And this one is called the lowest unoccupied molecular orbital. So it's the LUMO. So those are just some things to kind of remember. Okay. Which of the following is not an example of resonance? Okay, so basic resonance rules. Atoms can't move. So the first thing I'm going to look for is, did any atoms move? So, and the big thing that typically moves is if it's an implied hydrogen. So I'm going to draw my implied hydrogens in here. This has a negative charge, so it must have a lone pair. So that's why I didn't draw a third hydrogen there. Okay, this one has a carbocation, so there'd be 2 hydrogens here and 1 here. 2 hydrogens here still and 1 here still. Okay, this one, okay, there's no pi bond. And so just looking at this, I don't even have to look at see if there's any atoms. There's no pi bond. So that means there's only 1 pi orbital, and you need a highway of pi orbitals for resonance to work. So this one is a suspicious character, in my opinion. But if I draw in these hydrogens, there must only be 2 for that to be positively charged, and this one has 3. So we've had an atom has to move, so this one violates the rules, and so I'd say this one is not an example of resonance. And just to make sure, I check my last one. 2 hydrogens here, 1 here with this lone pair. 2 hydrogens here with a lone pair, okay, and 1 here. So, yep, I feel good about that. Which alkene would you expect to have the lowest heat of hydrogenation, which is the experimental way we can determine how stable it is. So we're looking for most stable. So this is going to be the one that has the most in conjugation, and that looks like this one to me. There's a gap between these 2 and this one. I'll highlight between these 2 and that one. There's a gap. These are all alternating. There's a big gap. This one's isolated. These are isolated. And this one's isolated with this gap right here. So answer choice 2. Which of the dienophiles is most reactive in a Diels-Alder? So dienophile is the one that loves a diene, is looking for a diene. So it's the double bond, and the diene has 2 double bonds. And the diene acts as the nucleophile in this addition, and this acts as the electrophile. So you should be looking for something that makes this more electrophilic, which means it must be electron withdrawing groups. So then when I look at this CH3, that's electron donating. This one I would say is a maybe. Like right off the top of my head, we haven't talked about that. So I'm thinking that probably isn't too different from a regular alkene. This one has 2 donating groups, so I'm going to say neither of these are great. But we're thinking which one is the most reactive. I'm looking at this one. Cyano groups are withdrawing because they have a carbon triple bonded to a nitrogen, which is really electronegative. And we have 4 of these, which makes me think this is going to be really reactive, but I'll double check this last one. Yeah, this is donating. So answer choice D. Okay, which of the following pairs of compounds could be used as a basis for Diels-Alder? So we need a diene, a dienophile. This one with electron withdrawing groups is good. This one with electron donating groups is good because it acts as the nucleophile. And it needs to be able to be an S-cis conformation. So this one is an S-cis. This one is an S-cis. Let's see. This one has I don't think that it has 2, it's CH, COO, CH3. So this has 2 single double bonds. We haven't seen a Diels-Alder with an oxygen, so that's not one that I'm real thrilled about. This looks good. Okay, so all these have dienes except for 2, so I'm getting rid of 2. And then the next thing I'm going to look at is, do they have the capability of being an S-cis? All of those do. Then I'm going to look at, do we have electron donating groups or electron withdrawing groups on which one? Oh, I just realized which of the following could be used as the basis for a Diels-Alder of the compound shown below. Oh, I was just going to see which one could even make a Diels-Alder reaction. That's what I get for going too quick. It's Sunday afternoon, and I want to go home, so I'm going too fast for you. Okay, that really changes things for me because that makes me think we're making 1 6-membered ring. I mean, these other things are still true, but we're making 1 6-membered ring. And it has to have, remember, Diels-Alder makes a 6-membered ring with a double bond on it. So we're making 1 6-membered ring with a double bond. And so when I look at this reaction, I'm seeing only one 6-membered ring with a double bond is this one right here. And so I can think, all right, we're going to break these bonds right here because, you know, if we number 1, 2, 3, 4, 5, and 6, the new bonds that form are between 4 and 5. And so when I look at this Diels-Alder, I'm thinking we have something of a starting material that looks kind of like this. But if your double bond forms there during the Diels-Alder, remember initially, I'm going to just number these over here, 5 and 6, 1, 2, 3, 4, 5, and 6. The new bonds that form, I'll highlight them in orange, are between 1 and 6 and 4 and 5. So right here, between 1 and 6 and 4 and 5. So those are the ones we broke. So then we also have a bond right here that would be where 5 and 6 are. So 1, 2, 3, 4, 5, and 6. So we broke that bond. But also in our starting material, there's a double bond between 1 and 2, and 3 and 4, and 5 and 6. So that's sort of the thing that I'm looking for. And then we know we have the CO2, CH3 off of it. So we need a structure that looks like this, and there's only one. So that gets us to answer choice D. But if you're not sure, you could also look, at what these would form. This already has one 6-membered ring, and it would form another one, but it would form another one right here as a bridge. This one would be a bridge. So this 6-membered ring that already existed would sort of be a bridge, so it would not give you that structure. And then this one is another good candidate, but it would, again, give you a bridge. So if you weren't sure, you need 3 6-membered rings, and they need to all be flat. Okay. What would be the following product of this reaction? Okay, so again, I think this is going to be a Diels-Alder, mostly because I just saw a Diels-Alder. But if you weren't sure, you could go through your reactions. First we learned acid-base, and this is not obviously acid-base to me. Then we learned substitution elimination. There's no clues that point to that for me. 3, addition of alkenes. Well, that is a possibility because there are alkenes here, but there's a lot of alkenes, which takes me more to our conjugated system. But just to make sure, I'll keep going through. After alkenes, we learned about reactions, radicals, and we learned about reactions of alcohols. And then we did conjugated systems. And one of those was Diels-Alder, and the other one was 1, 2, 1, 4. And then, let's see, conjugated systems. I don't know. I can't think of the next one. Oh, electrophilic aromatic substitution. And then we did oxidation reduction. And then we just got to the ketones, aldehydes, and carboxylic acids. So looking at this list, the only options that have any clues that point me towards anything is we have alkenes and they're conjugated. So then I'm looking, and we have a diene and we have a dienophile, so that narrows me in on Diels-Alder. So that's how I come to the conclusion that this is a Diels-Alder reaction. So I'm looking for those clues. And always in a Diels-Alder, what I actually do is I try to find this structure and the double bond. So the dienophile and the diene. And so this looks like my dienophile, and this looks like my diene. So I'm going to start by just numbering those. 1, 2, 3, 4, 5, and 6. So 1, 2, 3, 4, and then we have 5 and 6. And I'm not going to draw any substituents yet. I'm just going to go ahead and draw the mechanism. So we get a new bond formed between 4 and 5, and 5 and 6. So 1, 2, 3, 4, 5, 6. And then this double bond went right here. And then I'm going to draw in my substituent. So we had a bond, 1 carbon between 1 and 4. And we have this carboxylic acid, or not carboxylic acid, this ketone off of the other side. So I'm looking for a structure that looks like this. So I can immediately get rid of 1 because it doesn't have the bridged bond, and 2. These 2 are both good options, but this has 1 carbon in the bridge, and this has 2 carbons in the bridge. We only had 1 carbon in our bridge, so I'm going to go with answer choice C. And if, again, you weren't sure, you could eliminate 1 and 2 immediately because there's no 6-membered ring with a double bond, so we know that those wouldn't be Diels-Alder. So even if you're not sure, you can narrow it down some. All right, I'm going to need to go a little bit quicker. So as much as I want to walk you through my thought process on each of these, I think I'm just going to be a little bit less talking about through everything, and I'm going to go a little bit faster because I'm on a limited amount of time. I did do a similar quiz 8 last year in the fall of 2024, so you can go back and look in like November, December of 2024 and find that if you want, because I think I was more detailed through all of these. But so let's look at phenol. That's what I'm looking for first, is phenol. And then that's going to be number 1, 2, 3, 4, 1, 2, 3, 4. So only this one has 4-amino 2-bromophenol, so that's answer choice B. Which of these is anti-aromatic? Well, this is non-aromatic, straight up. These have lone pairs, but lone pairs can bend out of hybridization to avoid anti-aromaticity or to go into it, but these would be aromatic if they went into it, because there would be 6. So there's the unbroken ring of pi orbitals for each of these. Sorry, it's hard for me to go faster and not feel like so all these have the unbroken ring of pi orbitals, and the lone pair then could go into hybridization, which then would make all these aromatic. So this is my only choice left. And sure enough, boron does not have, if it's neutral, it has 3 on the periodic table, so it has an empty pi orbital and then no lone pair in it, so it can't go out of conjugation. So boom, that's my answer. Non-aromatic, this has a carbocation, so p orbitals all the way around. This has p orbitals all the way around, there's a lone pair there, p orbitals all the way around from that lone pair, carbocation. So those all have p orbitals all the way around. Even though this one's positive, if it was a carbocation, that would mean that it only had 3 things bonded to it. It had an empty p orbital. But for nitrogens, 4 things bonded to it, sp3 hybridized, that gives you a positive nitrogen. But that doesn't mean that there's an empty p orbital. So answer choice B. Aromatic, we're looking for, this has 4 pi electrons, so no. 4 pi, so no. This has a non-aromatic because there's a hydrogen there. This has 4 pi electrons, but a lone pair that could go into conjugation. And this has 8, so no. Okay, so answer choice D. Where's the compound shown below? Let me see. I have this, actually, I just finished making this, so I have it pulled up on my desktop. I don't know why it wouldn't be here. It looks like this. Okay, so aniline is when you have a this group. So I'm getting rid of those, which don't make sense at all. And then I'm just saying this is bromine, so, or this is the parent chain, so this would be ortho, meta, and para. So this is meta-bromoaniline. These, I know this is electrophilic aromatic substitution. The clues that point me to that is the benzene ring and the, I recognize these as the nitro, and so they make the NO2. So hopefully you remember that. Major product of the following reaction is, this is acylation. A lot of people had forgotten that one, but it goes very similarly in mechanism to our others. And so then the ring will attack. And when I'm looking at this, there's 2 possible benzenes that could attack. This one has a withdrawing group, but this one has CH3, which is donating. So I think it would attack on that side. And I think it would attack ortho or para to that parent chain. So that's what I'm looking for. And it would add the acyl group. So it would be something like this if it was ortho. Or sorry, if it was para, it would be like this. So that's what I'm looking for. So this one is on the side with the withdrawing group. This one also on the side with the withdrawing group. So I don't think it could be any of these. So I think it could only be this one or this one. And this one's meta, so no. And this one's para, so I think it's this. All right. I think we had a homework question on this that's very similar, but it's saying which of these would contribute to the resonance hybrid of the intermediate form of bromobenzene undergoes parachlorination. So we have bromobenzene, and it's not really attacking a Cl+, and it goes orthometa-para. So we have our bromine here. Actually, the curved arrow. I'm going fast, but the curved arrow should have gone from here. And so this and this are still unaffected. And so then we just see, are all these carbocations in a legitimate place? So if this arrow swung down, we would get this. And then the bromine lone pair could to give us that. So that's legitimate. Or if from this is the one we had drawn there, so that one's legitimate. And then if from here, if this swung up, we would get this. So I think all of these choices are correct. Propose a series of reagents to accomplish the following transformation. We've done a very similar one to this recently. But essentially, you could first do the nitration and get the nitro group, and then you could then do, in theory, something like this. But that wouldn't work well because your carbocation would likely rearrange. So adding primary on a Friedel-Crafts acetylation is hard, but also this is very deactivating. So I don't recommend you go that route. And instead, I would go the route of adding an acyl group where there's two carbons, one here and one here with AlCl3. So Friedel-Crafts acetylation, get you this acyl group. And then that is a meta-director. So then you could do the next step of H2SO4 and HNO3. And then you would have your this and your nitro meta to it. And then if you do zinc mercury and HCl, then that gets rid of that to get our final product over here. Alternatively, now you know several other ways you could do. So you could use Raney nickel and thiol, or you could use, there's another one that you learned, NH2 to make an imine with heat, and KOH to do a Wolff-Kishner reduction. All right, arrange the following in order of decreasing reactivity. So what is the most reactive in electrophilic aromatic substitution? Well, it's the nucleophile. So the most reactive is most electron donating group. So when I look at these, I'm thinking just broadly, this is electron withdrawing, this is electron donating, this is electron withdrawing, this is electron withdrawing, and this is electron donating. So I'm just going to go ahead and put these two on one side of the ring. You know, these are more reactive. And then these three are going to be less reactive. And I know that if you have a positive or a partial positive next to the ring, those are withdrawing, but it's even more withdrawing if it's a full-on positive. And nitro does have a positive charge. Nitro's Lewis structure actually looks like this. And so this is a very electron withdrawing group. So that should be my least reactive. So I'm just going to go ahead and eliminate any answer choices that don't have 4 as the least reactive. So that gets me down to these two. And the only difference between these two is one has the methyl group as the most reactive, and the other has the alcohol. Well, the methyl group doesn't have lone pairs, so it has less to donate. So I'm going to go with C as the right answer, and then I'll just double check. We have this as the most, and then this. Okay, I agree with that. We know we have nitro as the last, and so as long as acyl is before bromo, it is. Okay, great. I agree. All right. This deactivates towards EAS, but is still orthopara. That's an exception, so that would be the halogen. What is the IUPAC name for the following compound? All right, so the first thing I do, identify the parent chain. I found 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. So I'm getting rid of anything that doesn't have 8 in it. Okay. Well, that helps me out a lot. And then the next thing I'm going to do is I'm going to number. So it could go this way, or I'll draw it in a different color. Ketone is a high priority group, and if I go with green, then it is at position 4. So the parent chain is octane, and we have 4 ketone, which is 4-one. We drop the E and add the -one as a suffix, and then 2-methyl. And that's the only other one we have, so 2-methyl octanforone. Oh, that methyl is not 2. That methyl is 7. I forgot we were going with green. So that gives me this answer choice. 6-isopropyl. That doesn't make sense. We go with a simpler one. Okay. What is the correct structure for 3-phenylpropanal? Okay. Propanal is propane, but it has to have an aldehyde at the end. So 1, 2, 3 carbons. And on position 3, there's a phenyl, which means it's directly attached. There's no bend in it. So directly attached is a phenyl. So we're looking for something that looks like this. So let's just start by numbering 1, 2, 3 carbons. 1, 2. This is a ketone, so that doesn't work. This is a ketone too, so that doesn't work. That's acetophenone. And this is a ketone. So just by knowing Al is an aldehyde, that helps us out a lot. And then if you can count to 3, then you got it. So answer choice E. Okay, determine whether this is an aldehyde, ketone, alcohol. Okay, well, let's see. A carboxylic acid, I know, has a broad peak down here because it has so much intermolecular forces that it broadens out for the OH. Intermolecular forces are broad. And I don't see a broad peak like that. So I'm going to eliminate both the intermolecular force. Oh, wait. This also has intermolecular forces, but so does an amine, H with FO or N. So because none of these have intermolecular forces, none of them would have a broad peak. All of them would have a broad peak. There's not a broad peak, so I think it's answer choice D. But just to make sure, I'll double check with my IR shift table. And ideally on your exam, you're not going to be looking at your table all the time. Ketones typically show up around 1720, and that's what we have. So great. So I think that's perfect. So that's how I would approach your table, is don't rely on it because you only have 2 hours, but try to get the answer and then go back to it. Okay, what is the predicted product of the reaction shown? We're going to have an oxygen here and an oxygen here. I don't like that that's 1 and 2. I thought I got rid of that question, but I guess I didn't. Well, bummer. Okay. So O3 cleaves double bonds, and so we know that it will look something like this. And it's identical on the other side. And because it's O3, it won't, and it doesn't have another source of oxygens, then I'm going to go with right here. None of those make sense, so answer choice E. Which of the following is least reactive? Okay. Which of the following compounds is least reactive? So most reactive has more steric hindrance. So I guess the way I'm going to think about it is the least reactive has steric hindrance. And it's going to inductive effect, donate electrons. Okay, so the least reactive would have steric hindrance. So I'm going to say, of these, I'm looking at this has very little steric hindrance. All of them have 1 hydrogen. So we don't really care about that hydrogen. So then we're looking at the other side. This is substituted similarly to this. So both of these are going to have the inductive effect, and they're both going to be donating electrons. And this is also a similar shape, and it also is donating electrons. But I think this has a resonance structure in addition to just inductive effect, where we are able to move the positive charge around the ring so that we don't have a positive charge concentrated on that carbonyl carbon, which makes it less electronically attractive. So I think answer choice 1 is the least reactive. Which reagents are needed to carry out the conversion shown below? So we're going from a ketone to a hemiacetal. This is hard to isolate, so we would need only 1 equivalent of alcohol to do that. So that's what I'm looking for, and it should also be acid catalyzed. So this just looks like a super long chain with 1 alcohol in it, so that doesn't really make sense to me. Same thing here, and then this is just another ketone. We don't know how two ketones react with each other, so immediately I know it's A or B. And if we had 2 moles, we would get the acetal, so I'm assuming it's answer choice A. Ooh, okay, so right off the top of your head, you might not know what happens here, but if you think about the sort of tips about what we have an alkene. We don't just have one alkene, we have a conjugated alkene. And we only had one reaction that we did with conjugated alkenes other than Diels-Alder, and this can't be Diels-Alder because there's not a dienophile. But you can react it in the same way that we've reacted a lot of other alkenes, which is they'll be attracted to the acid because they have extra electrons and that doesn't have enough. And so the bond will break and you'll get a positive charge right here. So your hydrogen goes here. And then you have a resonance structure. And so this is 1,2, 1,4 addition. Your resonance structure looks like this. And so where your Cl- attacks depends on if we're under temperature control or not. So this is lower temperature, so there's less energy in it, which means it's just going to do the easiest thing, which means it'll do 1,2 addition. So your answer choice would be this. Now, if it had heat in it, if we had been able to put some work into it, it would produce the most stable end result, which would be the substituted alkene. So, and that would be the thermodynamic product. But this is the kinetic product. And we're not adding 2 chlorines, so you can get rid of that. So we have the thermodynamic product with the most substituted alkene or the kinetic, and so it's going to be answer choice A. Now, this is the major product. If it didn't have heat and it said all possible products, then I would say A and B, or 1 and 2. All right, what reagents are needed to carry this out? I'm looking at a nitrogen become an imine, and I know that imines form when we have a carbonyl carbon that reacts with a primary alcohol, and you do know the mechanism, but I won't make you draw it out. And we get NR. So I am looking at this double bond right here and saying like, okay, that must have used to been the carbonyl carbon right here. So it must have looked like this. 1, 2, 3 carbons, 1, 2, 3 carbons. Okay, so that's what I think we would need it to react with that. And if you're not sure, you can always do the mechanism to test it out. But they don't have the structure drawn, they have the name drawn. And so this is propane, because there's 3 carbons, and then we drop the E and add Al for aldehyde, which Al sounds like aldehyde, so I know it's that. So can't be ethanol because we need 3 carbons. Propanol, those are alcohols, so it's going to be one of these 2. Well, propanone is a ketone, so B is the right answer. Okay, and if you weren't sure and you just knew, oh, it's got to be, a ketone or an aldehyde, you could at least get rid of 1, 2 because they're alcohols, and you could get rid of 3 because you need 3 carbons. So you at least could have gotten down to a 50-50 shot. Okay, now this makes an imine. And what helps me to know what an imine looks like is I actually draw out the second to last step of the reaction looks like this. This would be right before your elimination reaction happens. And so your nucleophile would have to take this hydrogen, and that leaves this behind, and that goes there to make it all neutral. And then your nitrogen. And that helps me know what I'm looking for in my answer choice is if I draw out it's sort of like the imine right before you get to the enamine is how I think of this transition. But it's a positively charged imine, which is not good. So looking at all those, okay, well, first of all, I didn't even have to do that much work because we know that these 2 react and the nitrogen gets a double bond. And none of these nitrogens none of these have double bonds, and the one that has none of these have nitrogen. So that's how I'm eliminating 2, 4, and 5. And the one that does have nitrogen doesn't have a double bond, so answer choice A. Okay, and then when I see this, NH2, NH2, that's hydrazine, I believe is the name, and KOH and heat, this is going to be a Wolff-Kishner reduction, so I know it's just going to eliminate this. But then it's asking you to name it, so you need to be able to name. So 6 carbons is the parent chain. We have 6 carbons for all of these. But there's no alkene, so we can get rid of these enes right here. And there's no alcohol, so we can get rid of that. So answer choice A is the right answer. And you can always double check and make sure. 3-methyl, check, hexane. Yeah, okay, great. Oh, I don't know why this didn't fill in, but this is, you had this exact same question on your Kahoot or your quizzes. It was, I think, this plus this, and then rainy nickel. Okay, I don't know why it didn't show up. What is the predicted product? Why aren't these showing up? Oh, that's so annoying. The predicted product of the reaction shown is... Oh, okay. No, it's not benzene. Okay, so technically we haven't done this yet. Pyridine is a base. This is technically, we haven't done this yet as a recording of this video, but hopefully you can figure out what's likely to happen, which is this carbonyl could attack here. The oxygen wouldn't want to attack there. So, because it's a weak nucleophile and we don't have a way of protonating it, it's in basic conditions. So the pyridine, which is a base, can take this hydrogen and make this look like this. So then this could attack here and this could kick up. And then your leaving group would restore, or your carbonyl would restore and kick out your leaving group, and you would get this. So that would be, there's several different answer choices, but that would be the right answer. All right, the structure of the major product of the following reaction. So MCPBA we've seen twice. It makes epoxides, and it makes Baeyer-Villiger oxidation. So seeing that there's not a double bond for it to make an epoxide with, it must be Baeyer-Villiger oxidation, and it's going to pick the easiest thing to migrate, which is the hydrogen. So this would be your final product, which I believe is answer choice A. Which of the groups shows the stronger signal in an IR spectrum? So more polar is stronger signal. More polar bond. This fluorine is more electronegative than this chlorine, so I think this one would show. I don't know why it says yes. Compound 1 produces a stronger signal because fluorine is more electronegative than chlorine and produces a larger dipole moment. Oh, I think A. Compound 2 produces a stronger signal because chlorine is more electronegative. That's not true. Chlorine's not more electronegative, so I can eliminate that. Alkene group produces similar signals. No, that doesn't make sense because fluorine is more electronegative than chlorine. Alkene groups produce similar signals because both have vanillic halogen atoms. That doesn't make sense because the halogens are different. So there we go. Consider only the highlighted hydrogens. Oh, these didn't get hydrogen highlighted. Well, I guess they were highlighted by being drawn in. List the following compounds in order of decreasing acidity. So, all right, first let's just think about the pKa's that you may know. This one's 4 to 5. This one's 25. This one's 16 to 18. And then we don't know about these. I don't know if you have them on your pKa table. But something you can think about is the pKa would probably normally be around 50, but because there's a carboxyl or the ketone right next to it, would that make it more stable or not? I want to use the one that's like from your thing, but I don't have it with me. So if the base came and took this hydrogen, the lone pair that would be left behind right here would be able to then go here and kick up, which would make that more stable. probably not as stable as this carboxylic acid that has 2 oxygens, so that it can handle it more easily. But I'm guessing that this, therefore, is going to be more acidic than a normal alkene. And I'm actually going to probably put it up somewhere, I think it's probably like 19 to 20. And then I think, but let me see if that's on your pKa table. That would be my guess, but I want to make sure that you have it on your pKa table. Okay, yes, I'm looking at your pKa table, and there is a CH3 next to a carbon-oxygen double bond. It says CH3, CO, CH3, and it's 19.2. Okay, so there you go. Now, it doesn't have, oh, it does have. It even has a CH3, CO, CH2, CO, CH3. And it has that one around 9 to 10. So you'd have to look on your pKa table if you weren't familiar with these right away, but you can also assume that this would be more acidic than most things that don't have resonance structures. So this one doesn't have a resonance structure, and this one doesn't have a resonance structure, which is why I picked it at around 19 to 20. This has 2 resonance structures. Not quite as acidic as carboxylic acid, where it's immediately sharing the 2 lone pairs between the 2 oxygens. But it does have 2 options for resonance, which makes it very stable. So I'm going to say, first things first, is we know that this is the least acidic. So you can eliminate anything that doesn't have 5 as the last answer choice. And that gets you down to A and B already. So even if you didn't have your pKa table to look at, you could get to there. And then the next most acidic thing, if you think the next most acidic thing is carboxylic acid, then you can also eliminate that one. So this is going to be the only one that has carboxylic acid as the most acidic, and this alkene is the least acidic. So you could have saved time on that question. I should have approached it that way by looking at what was the most and least acidic and seeing what I could have eliminated. Okay, we haven't talked about enols yet. I'd like to before the semester is over. So this, it's called a tautomerization. It's not a resonance structure. Where this, it's sort of like an intramolecular reaction where this oxygen steals this hydrogen, these electrons come down here, and this kicks up. And because that oxygen stole the hydrogen, it's now bonded to that hydrogen. And then because these came here, now we have an ene, a double bond, and then this carbonyl-carbon bond broke to make a single one, so we get an alcohol. And so these, they're called tautomers, where they are interchanging, but they're not, they're in equilibrium. It's one molecule, but they're not resonance structures because atoms move. And this comes up a lot of standard tests, so I just wanted to go ahead and put it in here, even though we hadn't talked about it yet. Okay, amines. Which of these is a secondary amine? So let's find our nitrogen in all of these. Okay, well, this one has nitrogen with 4 things around it, so not that one. This nitrogen has 2 hydrogens, so not that one. This nitrogen has 2 hydrogens, so not that one. So one of these 2 is going to be our secondary amine. This does not have a hydrogen attached to it, so it's a tertiary, so B. What is the predictive product of the following reaction? Okay, so this is me giving you an opportunity to do some reactions of amines, even though you technically haven't seen it yet. But this is a way to make a primary amine become a secondary or a tertiary. Is the amine is the nucleophile in just an SN2 reaction. And so even if you haven't seen that before, you've seen nucleophiles attack and CH2, CH3, kick out the leaving group, so you'd get this. You would still have these 2, NH on here, and one would get deprotonated, probably by whatever your solvent is. You get HBr, and that would break up in your solvent. And then you could do it again to replace the secondary. 1, 2, 3, 4. The other one, so you get this structure. Is that right? 1, 2, 3, 1, 2. Yeah. This isn't a great way to make amines because they can like overreact, and then you'd get some with 2 ethyls and whatever. But it is a potential of a way to substitute out your amines. Predict the splitting pattern, integration, and chemical shift you would observe for each proton in this structure. All right, the first thing I'm going to look for is a plane of symmetry, which I see one right here. Well, I guess not right there, right here. So if I'm looking for these hydrogens, they would be the same. These hydrogens would be the same, and this hydrogen would be unique. But these would be the same as each other, and these would be the same as each other. So if I'm counting up my signals, I'd predict 1, 2, 3, 4. And then these 2 would be the same, so 5. And these 2 would be the same, 6. And then that one is 7. So there's 1 in that hydrogen right there. So 7 signals. This is messy, so I'm going to erase this and make it look cleaner. We're going to see 7 signals, and I'll give each one a letter, and I'll do some alternating colors. So A, and we'll give this one color, and then this one color, and then this one color, because it's 1. There's not a hydrogen on that substitution position right there. We'll give this, we'll give this one color. And then there is a hydrogen right here. Looks like the green, but I wanted to do this color. And then this one color. Okay. So we have A, B, C, D, E, and F. So 1, 2, 3, 4, 5, 6 signals. So I may have counted wrong initially. I think I maybe put a signal right there when there wasn't one. So I'm seeing 6 signals. So for each of these, I'm going to think about what they would integrate to. So we'll start with their integral. There's 1 hydrogen here. There is 2 hydrogens here. 2 hydrogens here. 1, 2, 3, 4, 5, 6 hydrogens here. 1 hydrogen there, and 6 hydrogens here. All right, as far as their chemical shift, the alkanes are going to be, I mean, it's not perfectly accurate, but they'll be in the 1 to 2 range. If they're off of an alkene, I think they'd be actually, or off of the aromatic ring, I think they will shift up to the left of that. So I think if there was a hydrogen here, that one I think would be all the way into like possibly 2 to 3. But in general, I just think they'd be shifted somewhat to the left. For my alkanes, they'd be somewhere between 0 to 2, probably to the left. 0 to 2, probably to the left. 0 to 2, probably to the left. Now for my aromatic rings, these show up from 6 to 8. Okay, and now if we're thinking about the splitting, okay, so this hydrogen has 2 neighbors. So 2 plus 1 equals 3, that's a triplet. These hydrogens have 1, 2 neighbors. So I think that would be 1, 2 neighbors. So that would also be a triplet. But also a lot of times benzene rings fall like really close to one another. So I don't know if and this would have 1, so I think this would be a doublet. But a lot of times these all kind of end up near each other, and this whole thing becomes a multiplet in real life. So I don't worry as much about benzene splitting. Okay, D does not have any, so it would just be a singlet, has no neighbors. E has 6 neighbors, so it would be a multiplet, a 7 split. And then F only has 1 neighbor, so it would be a doublet. Okay. Which of the following would be the strongest acid? Okay, so let's think about acids. These all seem to have the same basic structure of a carboxylic acid. You lose your hydrogen, and the electrons get left behind. And that results in, okay, this excess of electrons. So how well can you share the electrons? And so if we have a carboxylic acid, obviously it has 1 resonance structure here. But if we have this benzene ring over here, we also could have potential of this acting as an electron donating group, or if there's a resonance structure, which I can't draw out right now. But if this is an electron donating group, that would destabilize unless you have an electron withdrawing group here. So like if you had something that steals electrons, like these 3 fluorines, that would take electrons away and that would stabilize. But if you had something that's giving electrons, like 3 oxygens here, these donating electrons in are going to be doing the opposite of what we want. So we want a benzene ring with as many electron withdrawing groups as possible, but these all have donating groups. These are all methoxy groups, so the least methoxy groups is best, so I think this would be answer choice A. Okay. Again, I don't know what's going on here with this question. Okay. Compound has a molecular, I guess this is the question, it just stretched out this. Okay, so this is right, it just looks crazy. And this has a number 4 beneath it, and this has a hydrogen and an oxygen, and it has a number 5 beneath it. Okay, so molecular formula C6H12O2, IR spectrum, so that makes me think it probably a ketone, but potentially an ester, because ketones usually show up around 1710. And then in the Mars spectrum, 2 singlets, so no neighbors, 1.4 and a singlet. Oh, but we don't have the integral. The shift is singlet at 2. So it's not giving us a ton of information to go on. So I'm going to look and see what this would do. So I'm going to start just by looking at, do all of these have a ketone peak? And they all do, so we can't eliminate any. Or this carbonyl peak, so they all do, so that doesn't help us. Do they all have 6 carbons? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, they all have 6 carbons. They all have 2 oxygens. I'm assuming they all have 12 hydrogens. Okay. So its NMR only has 2 peaks, which means there's only 2 unique areas. So that's going to be the thing I think that gives it away. So for each of these, I'm just going to identify all their peaks. So this would be 1. There's a hydrogen here, so 2, 3, 4. So not that one. This would be 1, 2, 3, 4, 5. So not that one. 1, 2, 3, 4, 5. Not that one. 1, 2. No, that one doesn't have any. 1, 2, 3, 4. 1, 2. There we go. There's not a hydrogen right here. There's not a hydrogen there. There are 3 hydrogens here. And there are 3 hydrogens here, but they don't have any neighbors, and they would all integrate to 1. So the integral of this would be 9, and the integral of this would be 3. So answer choice D. Okay, what is the product of this reaction? So at the time of filming this, we haven't done this yet, but any carboxylic acid derivative can be converted back to the carboxylic acid. It, of course, is going to kick out the NH2, so you can kind of imagine it going something like this. And you'd get your NH O minus and your OH2 here. And then this comes back down and it kicks out this whole group. And so you'd have your O and then your OH2. And then your NH minus, but it would take the hydrogen from this positive charge. So even if we haven't done that, you should kind of be able to guess what would happen. Oh, I don't know why I had this OH2 attack. There's an OH minus right here, which would be less messy. So that OH minus would attack instead. So even if you didn't know, you should be able to do this. So we know we'd have carboxylic acid, 2, 3, 4 carbons, and then an amine. So 1, 2, 3, 4 carbons, and then an amine. But I don't know where it would have gotten another methyl, so that's not right. 1, 2, 3, 4, and then an amine. 1, 2, 3, that's not a carboxylic acid. This is a deprotonated carboxylic acid, and we don't have acid added to the workup, so that's possible. It would break open, so I don't think it would be this one. And then this, I don't even know where the other ketone came from. So answer choice B is one that makes sense. Okay, what is the IUPAC name for the compound shown? So your, what is that called? Your carboxylic acid has to be number 1. We have 6 carbons. We can get rid of anything with anything other than 6, so get rid of these. We've already got, so we just basically need 3 methyl, and that's good to go. Okay, following in decreasing order, most reactive to least reactive. Okay, so most reactive of a carbonyl carbon is going to be how attractive is the carbonyl carbon. So these are all carboxylic acid derivatives. And the other thing you can think about is how stable is the leaving group. So if I were to kick out, if I did a nucleophilic substitution where the nucleophile attacks, this kicks up, then it comes back down and kicks that out. I'd get Cl minus here, which is a very good leaving group. O minus, less good. NH2 minus, very less good. And then this structure. So NH2 minus, NH3 is already very reactive. So this is going to be the worst case scenario for sure. So I'm going to eliminate anything that doesn't have 2 as the most reactive. And then between chlorine and acetic anhydride, this would come up here. So this does have a resonance structure, which is good. But, so these are 2 good options for the most acidic. Or the best leaving group. But I'm going to see which one is the more reactive one by comparing their reaction with an acid. So we would get OH. This would be 4 to 5. And if we did Cl minus with H plus, this would be more than negative 1.7. So this one would be more reactive or more acidic. So this is less basic. So I think this is the best leaving group of all of them. So I'm going to go with that being the more reactive. So I'm going to eliminate this and do answer choice E. Okay, examine the following IR spectrum. Which oxygen-containing functional group is most likely present? Okay, well, 2 big things stick out at me. This is a carbonyl, no question. And this big broad thing makes me think of an alcohol, but often when the carbon stretching is within that super broad thing, that's because it's from a carboxylic acid. So I think this is a carboxylic acid based on that unique structure. Okay, and then last but not least, what is the predicted product of the reaction shown? So we've already decided, actually, based on the last question, that this is a better leaving group than this. So it's going to attack and kick up. And you would get O minus, your chlorine, and a new bond to this whole thing. Hopefully I have the right number of carbons there. This bond will come back down and kick out, and so you'd end up with... would kick out your chlorine, not this thing, because the chlorine's a better leaving group. And then however many you get. So this is totally wrong. There should be an oxygen as the nucleophile. Same thing here. So this is the only possible option. So answer choice A. All right, I think that's all of them. Sorry for the super long video, and sorry I wasn't able to go in as much depth as I normally would. But I hope this was helpful for you as a video key, and good luck studying.